of section 3.2, page 233, we are going to continue talking about logarithms, but we're going to look at a specific type of logarithm. You might remember in section 3.1 when we talked about exponential functions, the first day of that lesson we talked about exponential functions in general and how they worked and what their graphs looked like. And then the second day on 3.1 we looked at a specific type of exponential function. It was an exponential function with a base of e. And we said e is the natural base. It's 2.7182812 and 1828, and then it goes from there where it deviates. So it is non-repeating and non-terminating. It is irrational. So very much like pi, we assigned it e so that it was easier to work with instead of having to work with that irrational decimal all of the time. And so we said that when you had an exponential function with a base of e, that was the natural exponential function, and then we had all kinds of applications for that. So if logarithms and exponentials are inverses of each other, then it makes sense if there was a natural exponential function, then we should have the inverse of that. We should have a natural logarithmic function. And so that's what we want to look at for the second half of section 3.2, continuing with logarithms, but specifically the natural logarithmic function. So if we go back to the relationship between an exponential and a logarithmic, all right, if we have y equals e to the x, that's the natural exponential function, an exponential function with a base of e. If I switch x and y, because remember for inverses x and y switch places, then I would get x is equal to e to the y. And if I switch from the exponential form to the logarithmic form, then that is the definition that they give us there on page 233 for the natural logarithmic function. So we can see how this really is the inverse of that natural exponential. It's a little easier to see when it's in its exponential form than in its logarithmic form. So we joke all the time about mathematicians being the laziest people on the face of the earth and how we have an abbreviation for everything. Here's yet another example. We want an abbreviation for the natural logarithm because we use it so often. And we already are using a log with no base at all for the common logarithm, a base of 10. So we needed to come up with something different. And so the abbreviation that we use for the natural log, which is a log with the natural base of e, is just ln. Easy way to remember that is it's kind of like natural log, that would be nl, but it didn't look right that way, so you reverse the order. Ln looks a little more like a log would starting with that l. So when you see ln x, that's the same thing as the log base e of x. Now, we learned yesterday that you can't take the log of a negative number or of 0. What you take the log of has to be a number greater than 0, so that's going to be true for our natural logarithmic as well. So if we saw something like the log base e of 2, that would be the same thing as ln 2. Or if they gave you something like ln 2 and you wanted to, you could rewrite that as the log base e of 2. They're the same thing. Those are equivalent. So yesterday they had given us in the first half of this lesson all these properties of logarithms that applied when you had a log base a as long as a was a number greater than 1. Well, e is a number greater than 1. So all those properties that we learned yesterday about logarithms are going to apply here. So let's go back and let's rewrite each of those properties from yesterday. Instead of writing it as log base a, let's write it as log base e. And if we want to write it as log base e, we also could abbreviate that as ln. Okay? So we saw yesterday that if you take the log of 1, no matter what your base is, as long as it meets the requirements for logarithms, that answer is always going to be 0. So that'll be true for a log base e as well. So ln 1 would be equal to 0, or log base e of 1 would be equal to 0. And you can see if we switch it to its exponential form that we can see that's true. The second thing is that we said if you had a log where the base and what you were taking the log of were the same number, that answer would always be 1. So if I have the log base e of e, that's going to be 1, and since log base e can be written ln, then ln e is always going to be 1 as well. All right, then we said that if you took the log of an exponential and they had the same base, that the log and the exponential being inverses would cancel each other out. That's that composition of inverse functions. They cancel each other out, they undo each other and take you back to what you started with, which is just the x. So if I have the log base e of e to the x, that drops out and just gives me x. So if I replace log base e with ln, then ln e to the x would just give me x. The other composition of that would also hold true. If you take the exponential and you raise it, natural exponential, and you raise it to the natural logarithmic, they'll undo each other, they'll cancel each other out, and they'll take you back to what you started with, which is just x. And again, if we switch that from its exponential form to its logarithmic form, we can see we get an identity, so we can see that's true. And then the last one said that if you have two logs that you're told are equal to each other and their base is the same, which of course here we have a base of e, then that means that what you were taking the log of has to be equal as well. So that would mean that x would have to be equal to y. All right. So example number 7, they asked me to find ln 2 and ln negative 1. And they asked me to evaluate those on my calculator. So grab your calculator if you would, scientific or graphing. If you want to try it in both to make sure you can do it on both, that's fine too. So in the first half of this lesson, we saw how to take the log of a number. So now we can see how to take the natural log of a number. So the first one they gave me there was the natural log of 2. So your ln button is right here, right below your log button. So I can just say ln 2. And we've been rounding those to 3 decimal places, so we could say 0.693. All right, what if you try to take the natural log of negative 1? What do you get? Yeah, I get an error statement, non-real answer, or sometimes when I'll put a value in, it'll tell me that there's a domain error. And again, that goes back to that idea that you can't take the log of a number that's less than 0 or equal to 0. So if I ask my calculator to take the log of 0, the natural log of 0, the log of a negative number, the natural log of a negative number, it's always going to give me an error message for that reason. All right. Look at example 8. For example 8, they want me to evaluate these natural logs without a calculator. So that means I need to be using those properties that we were talking about over here, or maybe I evaluate them the way we did in the first half of this lesson with our logarithms. Either way. So to begin with, if I have ln 1 over e, I'm going to rewrite that as e to the negative 1. Remember, to move across the division bar to get that e from the denominator up to the numerator, I use the negative exponent. So it was 1 over e to the positive 1. Now it's e to the negative 1 over 1. Two different ways that you could go about this. We had a property up here that said if you have the natural log of an exponential to the x, because those are inverses, the composition of those will cancel each other out and just leave you with x. So literally for this problem, I can look at it and say, okay, ln and e are going to undo each other, and my answer is negative 1 by that property. Now, I could work this the way that we did the first half of this lesson. When we were working with logs yesterday, when we saw a log, the very first thing we did was we switched it to its exponential form, right? So if I had ln e to the negative 1, ln of course is log base e, I could switch that from its logarithmic form to its exponential form. So that would be e to the x equals e to the negative 1. And then we were going through and saying when your bases are the same, you can set your exponents equal to each other. So since my bases are the same, I could set my exponents equal to each other, and I would get that same negative 1. So I can work this the exact same way that I did yesterday, but I also can take a major shortcut if I use that property. Okay? So either way you want to go for this next one, ln e to the second, what are you going to get? Either way you want to go, either the property or working out, ln e to the second, what are you going to get? 2. Because ln and e would cancel each other out if I wanted to do that property. Or if I wrote it in logarithmic form, I would have log base e, so e to the what equals e squared, and that would also give me 2. How about the next one, ln e to the 0? 0, right, because ln and e could cancel each other out, or if you said e to the 0, that's 1, that would leave you with ln1. That's another one of our properties, that ln1 is equal to 0. That would take me there as well. All right, for the next one, I have 2 ln e. So let's figure out that log first. What's ln e? What's ln e? 1. Because you could say ln e is 1 by this property, or you could say this is ln e to the 1, so ln and e drop each other out and leave me with just that exponent of 1. Either way, then I would have 2 times 1, which is 2. And if I wanted to check myself, I could throw each of those into my calculator and verify that those are the answers that I get. All right, look at example 9. Example number 9, they say find the domain of each of these functions. Now, we've talked about the fact that you can't take the log of a negative number or of 0. You can only take the log of a number greater than 0, right? So if I want the domain, I'm going to come down here and say what I'm taking the log of has to be greater than 0. That's what they told me right up here. Whatever you're taking the log of, in this case it was x, whatever you're taking the log of has to be greater than 0. So to find my domain, I'm going to take whatever I'm taking the log of and set it greater than 0. And that's for a common log, a natural log, any log. Whatever I'm taking the log of, I need to make that greater than 0. And then I can solve that to find my domain. So what am I going to get? How do I solve that? Add 2. And so I could write it as x is greater than 2. Or if they wanted interval notation, I could say to infinity. All right, look at the next one. For the next one, I have the natural log of 3 minus x. And again, they want the domain. So what am I going to do? Why would I do that? Okay. Okay. We're going to set it greater than 0. I don't want to set it equal to 0 because I can't take the log of 0, right? But let's take whatever we're taking the log of and make it greater than 0. Whatever we're taking the log of, greater than 0 every single time to find our domain. And so then, yeah, at this point we could go through and multiply by -1 if we wanted to, or you could move that x to the other side, whichever way you want to go. If you multiply both sides by -1, don't forget you have to reverse your inequality sign, right? Anytime you multiply both sides by negative. So you absolutely could do that. For some reason, we tend to like the x on the left-hand side, so I could turn that around. Instead of saying 3 is greater than x, I could say x is less than 3. You can turn it around as long as you keep, like right now, you've got the big N towards the 3 and the little n towards the x. So when you turn it around, make sure it's that same way. Big N towards the 3 and little n towards the x. And then you won't mess it up. So 3 is greater than x is less than 3 means the same thing. Or I could write that in interval notation. All right, example number 10. Example 10 says students participating in a psychological experiment attended several lectures on a subject. At the end of the last lecture and every month for the next year, they were tested to see how much of the material they remembered, and the average scores for the group were given by the human memory model. And this is the equation they give me for that human memory model. F of t, because t is our time that's passed, f of t is equal to 75 minus 6 ln t plus 1. And they want to know 3 things. What was the score like immediately after the information was taught? Like how much did they retain? That kind of gives us a baseline. What did they know to start with? And then how much did they remember after 2 months? And how much did they remember after 6 months? All right, so let's start with immediately after the teaching was done. No time has passed at all, so we can say time is equal to 0. So we could plug that in. So we're going to put 0 in the place of t. So we'll get 75 minus 6 ln 1. What's ln1? 0, right. So we would get 75 minus 6 times 0, or 75. So they knew 75% of the information immediately after it was taught. All right, then they came back and they tested them again after 2 months to see how much they remembered. So this time we want our time to be 2. So let's take 2 and plug it in the place of t. So 75 minus 6 ln t plus 1, 75 minus 6 ln 2 plus 1, putting 2 in the place of t. Now, there are times when we're working on a test or a quiz where we don't have a calculator. Like we don't have a scientific or a graphing. We don't have something that has a log button or a natural log button on it. If that's the case, then this is my answer right here, because I don't know what ln3 is. That's not a value that we can figure out without a calculator. But if I do have a scientific or a graphing calculator at my disposal, then I could go ahead and throw that in. And I find out that they retained 68.4% of it after 2 months. All right, so what are we going to do to figure out how much they knew after 6 months? Plug in 6 for t, perfect. So if we put 6 in for t, again, if I didn't have a calculator with a log or an ln button, then this would be my answer right here. But if I do, I can go ahead and type that in. And after 6 months, they remembered 63.3% of the information. All right, so here is our homework on pages 236 to 237.